Good morning, everyone. It's working. Fantastic. I'm not hearing myself, so I hope you forgive me for talking like this. It's a great honor to be here and introduce the Nobel Prize winner visiting us this year, Michael Kosterlitz. Many of us have been reading his papers and using his results in our everyday life, and that is, of course, a privilege to actually meet the people behind the papers. And that is something that I think it is fantastic that we do here, that we actually have this possibility. Now, we are building the wall of science, where we're all hopefully putting a little bit of a grain of sand in, and then hopefully this wall will continue to grow and be beautiful. Now, many of the things that connect to this event are quite spectacular. First of all, he's not American, he's British. And he was working in England when he actually was doing the work that he's honored for now. And I think this is important. Now, I would also like you to take a notice of the papers that are actually the basis for the prize. They were published not in Nature, not in Science, but in Journal of Physics C, Solid State Physics. And the second one, Journal of Physics C, Solid State Physics. So remember, it is not the glossy front page that makes a difference. It's actually the content, and I'm looking forward to hear more about it. Welcome.
Thank you all very much indeed. Is the microphone on? I can't really hear.
Now, all right. I'm definitely technically challenged when it comes to slideshows like this. So I thought I'd start by telling a little bit about the story, how this all came about. I was actually started life as a high energy physicist, and I'd ended up as a postdoc in Torino in Italy, doing some complicated calculations on something that wasn't getting me anywhere. So then anyway, I decided that the thing to do after Torino was to go to CERN, because CERN was the premier place for high energy physics. Of course, being my usual self, I procrastinated and failed to get the paperwork to CERN on time, so I was turned down. All right, so here I was in Italy, unemployed, or at least facing unemployment. So I needed a job. So I dispatched on my wife, or the lady who's now my wife, went off to walked down to the station, bought an English newspaper, and we looked for job adverts and found a couple and applied for them. And then so eventually I found myself in Birmingham. Now, at the time, Birmingham University was the last place I wanted to go, and I wasn't very happy. But as it turned out, it was the best thing that ever happened. Because at Birmingham, after I was working for another year, getting nowhere on continuing calculations on high energy physics, I got very fed up, and then went round the department, visited every office, asking people if they had some sort of problem that maybe I could look at, and then found myself in David Fowler's office, where I stood there as he explained about all sorts of things I knew nothing about. Vortices, superfluids, dislocations in solids, all sorts of new and strange things in physics. However, what he was saying somehow made sense to me. And so I thought, maybe we can do something with this. Or at least, perhaps I could actually join in and do something here. And so really, you could say the rest is history, because David and I started working on these two-dimensional problems. And basically the motivation was that there were some rigorous theorems floating about on which said that long-range order in two-dimensional crystals and superfluids was not possible. And that seemed to preclude the existence of a two-dimensional crystal or a two-dimensional superfluid. I mean, of course, but however, there was an experiment staring us in the face. Now, let's see if I've got these slides arranged in order. Yeah. Here's the experimental evidence that was staring us in the face. You notice this is from a 1972 Fizerev letter. And this is what this diagram, what this graph shows is on the horizontal axis is basically the total amount of fluid absorbed on the surface of a resonant crystal. Okay? And of course the fluid I'm talking about here is helium-4. And the vertical axis is the reduction in resonant frequency. And of course, as you all know, the resonant frequency of a crystal is inversely proportional, basically decreases as the mass increases. As the mass of the resonating crystal increases. Now, let's suppose that for a moment that the helium being absorbed on the surface simply sticks to the surface. Okay, and we're always talking about a very thin film, maybe maybe maximum 2, 3, 4 layers, atomic layers thick. So if the fluid is sensible, like water, you'd expect that every atom or molecule of fluid that gets absorbed on the crystal surface will just stick to the crystal, and if the crystal vibrates, the fluid will vibrate with it because it's stuck. And therefore the resonant frequency, the mass of the resonant crystal will effectively increase, therefore the resonant frequency will decrease. And yes, that's what happens to start with, because this horizontal axis simply tells you how much fluid, helium, is actually absorbed in the crystal. And the straight line tells you how the resonant frequency should behave, assuming that all the fluid is stuck to the crystal. But you notice that yes, as you absorb more and more fluid on the surface of the crystal, yes, exactly the expected, it behaves exactly as expected, until suddenly some of the fluid seems to not stuck to the crystal. There's a deficit. So the deviation of the experimental data, which are the little dots from the straight line, is a measure of the mass of the fluid that is decoupled from the crystal. In other words, it's not vibrating with the crystal. So you have to say that's superfluid because it's simply decoupled from the motion of the crystal. So this piece of experimental evidence was staring us in the face. Of course, being an ignorant high-energy physicist at the time, it took me a while to understand what the curves meant. But when I did understand what it meant, then this piece of experimental evidence was saying shouting very clearly, there is a phase transition. You can just see it. And so that meant that we have a discrepancy between observation and the interpretation of the rigorous theorems about two-dimensional systems of this nature. So there were two possibilities. Either the rigorous theorem was wrong, or at least misinterpreted, or the experiment was wrong, or both were wrong. And so, under circumstances like that, the safest bet is that the experiment is right, and any mathematical theorem you have is either wrong or you're misinterpreting it. Now, these rigorous theorems were pretty simple, and it was difficult to see how they could be actually wrong. Therefore, the only sensible conclusion to be made was that the rigorous theorems were being misinterpreted. And so, after all, the experiment was telling you, look, there is a transition here. Something's happening. Some of the fluid is decoupling from the crystal. And so, if it's decoupling, it's not moving with the surface of the crystal, it must be a superfluid, something that flows relative to this crystal without any viscosity. In other words, there's a phase transition in this thin film of adsorbed fluid. So, we now have this major discrepancy between the interpretation of the rigorous theorems and the experimental evidence. So, what does one do? One has a problem on one's hands. And so let me just try to summarize what was known about two-dimensional systems in the early 70s when we were faced with this apparent discrepancy. So the standard theoretical model to study phase transitions and so on took magnetic systems. And the magnetic system can always be mapped into some real physical system. And the standard problem is, you have this, remember we're doing statistical mechanics, and the essential thing about statistical mechanics is you calculate the energy of some configuration of the system, then you multiply this energy by 1 over the temperature times some dimensional constant, put this quantity in an exponential with a minus sign, and then simply sum up over all possible configurations. That's statistical mechanics. And then that gives you the partition function from which you can compute any physical quantity you want to. So, very simple. So this is that energy I write down there is a model which covers a huge number of possible systems, and it can always be interpreted, mapped into some real physical system. So we have got a set of animals S lying on lattice sites denoted by the eyes and so on, and these S's can have any number of components. It's a vector with any number of components you want, and this system was the subject of a huge number of studies because it's a very important system. So the question is what's known about them, and the methods of investigating such a system is exact results, which is not easy. Monte Carlo simulations, numerical Monte Carlo simulations, and analytic work, and high temperature series expansions. And so N denotes the number of components of your spin, of this spin S, and we know that it was well known that for N equals 1, that's called the Ising model, that there was an exact solution existing, done by Onsager back in, 1947, something like that. And yes, that's an exact solution, and yes, that had a phase transition. In other words, if you lower the temperature enough, suddenly bang, you have a state with zero magnetization, and then suddenly bang, temperature gets low enough and you have a macroscopic magnetization. So that has a phase transition. If you make the number of components, the spin components 2, then there was no exact solutions, and there were some computer simulations, and the results were basically, maybe it has a transition. It might have. And if you put have more spin components, 3, 4, etc., again, the only information we had were numerical simulations and high temperature series expansions, and the results said, well, probably not. There probably is no phase transition in 2 dimensions. And then if you take the number of components of the spin, take the limit of an infinite number of components, that can be mapped into an exactly solved problem, and the answer there is no. There is no phase transition at any finite temperature. Okay, so that was the rather confused situation David Thales and I were faced with. And in particular, the system of interest was the n equals 2 system, because this is precisely the problem of a 2-dimensional superfluid helium. And so we had this analytic or numerical result. Perhaps there is a phase transition there, maybe. And we have the experimental result, which says, don't be silly, yes, there is a phase transition. And so the theoretical problem we're faced with is trying to understand, in particular, this particular situation with 2-component spin and trying to explain the phase transition. Now, remember what the problem now is. We know there's a rigorous theorem which says there is no long-range order. Now, there's no magnetization. And according to Landau, which is which was the Bible about phase transitions in those days, Landau said that a phase transition is from a high temperature phase with no, complete disordered, to a low temperature phase with long range order. But here's a system where rigorous theorem says there's no long range order at any temperature, but experiment says, okay, maybe there's no long range order. I don't care, I'm an experiment, but there is a phase transition here. So that's a problem we had to face, or we had to resolve this apparent conflict. And so we sat down, or at least I stood and stared at bits of paper, not knowing what I was doing, but I think this is... But we sort of eventually came to some sort of conclusion. Now, and of course, David Thales was a guy who knew everything about everything, and he had all the fundamental ideas, basic ideas. I was just the stupid, the ignorant postdoc assistant who, was sort of could think, but was very, very ignorant. But remember, I had gone through a training for high energy physics, and as a high energy physicist in a graduate school, I dismissed all this condensed matter, solid state stuff as being not of no interest whatsoever. And so I didn't bother with things like statistical mechanics and so on, because that was not field theory. However, in talks with David, I realized that, look, statistical mechanics is actually a really fundamental theory where everything relies on statistical mechanics. And so we were faced with the following problem. We could simplify the problem to, okay, so we take our spin variables, that are variables in each site, and write them as an amplitude, call the x component of the spin amplitude times cosine theta, because obviously the spin can point in any direction. And the y component of the spin is just the amplitude, or the length of the spin, times sine theta. Or we could write it in terms of the so-called superfluid order parameter, which is just s sub x plus I times s sub y, which we written as an amplitude mod psi times ETI theta, where theta is the phase. All right, so then in principle you can write down the Hamiltonian, assuming that neighboring spins are almost parallel to each other and expand, and you get just the energy is just basically proportional to the integral of the over the film two-dimensional plane of the gradient of theta all squared, which seems very simple. In fact, if you like, it's a trivial Gaussian problem, which you can immediately write down everything you know, everything, you can calculate everything, and it's very boring, nothing happens. However, then we realized that we'd missed something. Because actually, the energy, which can be written as in terms of the cosine of theta I minus theta j, is actually a periodic function of the angle, because every time the angle, one of the thetas changes by a multiple of 2 pi, the energy must go back to what it started as. And therefore, we can say that, look, we have some topology to worry about. Okay, now, you don't need the fancy word topology, because you can do without it by saying, all right, there are some excitations in this system which have high energy, and they're complicated, but there is a possibility that if you take some point in your system and walk around this in some circle or any shape you want to, and you ask the question, how much does the angle, the phase change as you walk around this closed contour and come back to where you started? That can be a multiple of 2 pi. Because the order parameter is ETI theta, proportion ETI theta, and e to the 2 pi I n is 1. So certainly the order parameter, or is single valued, as it must be. And so these excitations are permitted. And you work out the energy of such an excitation in a system of, say, L by L system, and look, you get, it's rather large energy. It's proportional to the logarithm of the system size divided by some microscopic cutoff, say a lattice spacing or something like that. And you think, okay, that's too big. So obviously such excitations can't exist. And then you think a bit deeper and you say, now wait a minute. This quantity called entropy. Because remember, the essential quantity you want to calculate is the free energy, which is energy minus temperature times entropy. And the entropy is proportional to the logarithm of the number of possibilities, possible positions of the say the vortex center. So we have to now talk a little bit about what a vortex is, and it's I had this beautiful picture of a vortex somewhere. My slides seem to go all muddled up. I apologize about that. I mean, all a vortex is you have a central point about which the fluid is rotating round and round. And of course, obvious at this point, if you think that the velocity of the fluid is proportional to 1 over the distance from the center of the rotation. And it's clear that as you go towards the center, the velocity of the fluid has to go to infinity, and that is ridiculous. Things don't go to infinity. Therefore, the center of the vortex cannot be any longer a superfluid, right? The fluid that flows without any friction. And it's either not a superfluid or it's nothing there, one or the other. Doesn't really matter. And so one has to associate. So you can say that the number of possible, the entropy of the vortex is proportional to the logarithm number of possible positions of the vortex, which can be parameterized by the position of this vortex center. And that is just proportional to, that is just, the number of possible positions is just the area of the film divided by some microscopic area. And so we can write the entropy of a vortex as the Boltzmann's constant, to get the dimensions right, times the logarithm of L squared over A squared, where L is the linear dimension of the system. And so, remember, the central quantity in statistical mechanics is the difference between the energy and the entropy, and both energy and entropy diverge like the logarithm of L over A, which is a very large number indeed. But we can write, but the free energy was E minus temperature times entropy is just proportional to, the proportionality of the logarithm is just pi j, where j is, say, the exchange interaction in the magnetic language, minus 2kt times logarithm of L over A, the system size divided by microscopic length, which can either go to plus infinity as the system size goes to infinity, thermodynamic limit, which you've all heard about, or minus infinity. And so the probability of a vortex is proportional to e to the minus beta times the free energy of a vortex. And so it becomes system size divided by microscopic length times the power of minus pi k minus 2, where k is just, say, the exchange constant divided by kt. It's a temperature-dependent animal, anyway. And so, if at k depends on temperature, basically, k is large at low temperatures and small at high temperatures. And so, the probability of having a vortex is L over A to the power of minus pi k minus 2. The minus 2 thing comes from the entropy, and this pi k thing comes from the energy. And so the probability of getting a vortex goes to 0 at low temperatures, where the temperature is such that pi k is large, and when the power is negative, the probability is basically 1. I've ignored normalizations. And so you can say the probability of this vortex appearing is 1 at high temperatures, or if you like, pi k less than 2. Now, that's the essence of the calculation we did. It's actually not very difficult. And it's amazing that basically this is the what we got the prize for. Now, of course, one can go a little bit further. I mean, obviously, if that's all we'd done, nothing would have come out of it. But one can go a lot further, and one can. So let's look at some of the crucial predictions of a slightly more sophisticated theory. And the idea is that you can write down the Hamiltonian as, well, the Hamiltonian the energy divided by Boltzmann's constant time temperature is just this half K naught, where K naught is a quantity, is a temperature-dependent coupling constant, times the integral of the gradient of the phase all squared. And this is all very well, but we have to relate this to physics. And if you think in terms of the superfluid film, the essential, a physically measured quantity is the so-called superfluid density. Now, the superfluid density is a funny quantity. It happens to have the dimensions of mass per unit area, hence density, but it's actually a rather complicated response function. So you don't want to think too hard about this, because if you think hard about what all these things mean, your head is liable to explode. So don't think too hard about it. But the essential thing is that the quantity you actually measure physically is related to, I call K sub r, which means the renormalized stiffness, if you like. And this renormalized stiffness is basically the measured superfluid density, what you measure by an experiment. And this depends on the bare coupling constant, that K naught in the first line, and it also depends on another quantity called this Y, called the fugacity, which is related to the probability of this vortex excitations being there or not. So the real quantity you want to calculate is a function of K naught and Y naught, the parameters that appear in your energy. But then you apply this fancy renormalization group method, and you wave your hands and say all sorts of magic words, and eventually you find that if you, suppose you try to replace, do what's called a renormalization group calculation or transformation, where you try to relate the actual physical problem to another problem calculated at a longer length scale. In other words, you say that your microscopic cutoff, which is, say, the vortex core size, E naught, you try to relate this thing to a new problem where you make just make the vortex core size larger by a factor e to the L. And so what you end up with is, with this renormalization group calculation, you end up with a new theory relating the old problem, the real problem, to a new problem calculated in terms of the same problem, but at a longer length scale with a new longer cutoff, which is parameterized by this parameter L. Now, this is called the renormalization group transformation, which at this level is content-free, because all it's saying is, I have this problem I want to calculate, I can relate it to another problem at a different length scale, but I've got the real calculation somewhere, because I don't know anything. So all I've done is related one insoluble problem to another, the same problem, but I mean the same insoluble problem, but with different parameters. And so you say, okay, fine, but how do I get any information out of this? And so you with a bit of luck, you realize that just maybe, if I continue this transformation for far enough, like to very large cutoffs, perhaps I can actually solve the problem. And this happens to be a situation where you can. For example, if you let this rescaling factor L go to infinity, you end up with the physical quantity you want to compute with the physical parameters k0 and y0 to the same problem when you take this scaling variable off to infinity, k infinity, the same problem calculated at when L goes to infinity. You say, all right, that's not very useful. But in this case it is, because it turns out that if you are below the critical temperature or at the critical temperature, this parameter y, which is the one that makes life very difficult, actually goes to 0. And so, then you can calculate this quantity when at infinity, and it turns out, to one's great surprise, that when this fugacity y is 0, that the physical measurable quantity is just this coupling constant measured at L equals infinity, which is not hard to calculate. And if you're at the critical temperature, this number is actually 2 over pi. So what we have is, we have this exact prediction that the measured superfluid density, this rho with the renormalized superfluid density, divided by, measured just below the critical temperature, divided by the critical temperature, is given in terms of some physical constants, which are exactly known physical constants, which is works out to be exactly 3.491 times 10 to the minus 8 grams per square centimeter per degree Kelvin. Okay, that's all very well, but so what? Then, to our surprise and great pleasure and great surprise, the measurement was done. And here is a graph of the experimental results, courtesy John Reppy, David Bishop and John Reppy, who did the measurements, or finished the measurements in 1978, which was 5 years after David and I did our work. And here we have the superfluid density, the measured superfluid density just below the critical temperature, plotted against the critical temperature. And the dots represent the experimental results from a variety of experiments. And this graph, or at least the dots, were plotted before the authors learned of the analytical work, which was actually done by, this analytical work was actually done by David Nelson and myself. And so and the prediction that David and I made concerned the slope of said that the superfluid density at just below Tc was proportional to the critical temperature. And the proportionality constant was known. At least we predicted what this proportionality constant was. And when they drew the straight line with our predicted slope, it goes right through the experimental data. There's that straight line is the the theoretical prediction. Now, I think that this graph is actually good is good confirmation that the theory is right. It may not be the only theory that's right, but which makes this prediction, but it's certainly the only one around at this point. And so this is our evidence that the confirmation for the confirmation of the theory. Let's see. Okay. Now the other system in which these so-called topological excitations are important are in two-dimensional crystals, because in superfluids the topological defects are these vortices. In two-dimensional crystals, the topological excitations which are important and which will control the analogous mechanism or the analogous transition are dislocations and disclinations. Now, Dave and I attempted to work out the theory in this situation, but unfortunately we messed up because we knew about dislocations in crystals, but what we missed was the fact that dislocations are not enough to melt the crystal. Now, okay, so perhaps I should back off for a second and explain why these topological excitations, vortices in superfluids, are so important. Okay. I think superfluids are easy to understand. Okay, what is a superfluid? It is a fluid that moves without friction, without viscosity, or no dissipation. What does this mean? Imagine you have a flowing superfluid, a flowing film of superfluid, and if it is superfluid, this flow will keep going forever. Persistent current, it won't dissipate. So then we have to ask, so what can happen? What can dissipate this? What can cause the superfluid to slow down? What can dissipate the flow? The answer is, the only thing that can dissipate the flow are these vortices in the superfluid. And what do the vortices do? Well, how can they dissipate the superfluid? Well, it's easy, because if you take a vortex and you simply send it across the system at right angles to the flow, it will reduce the superfluid velocity. So that's fine. But where do these vortices come from? Well, why should they exist in the first place? Well, again, we wave our hands and utter the magic words, statistical mechanics. Because think about what happens in a superfluid at finite temperature. At finite temperature, statistical mechanics tells us that everything that can happen will happen with some probability. And every possible excitation that can occur will occur. And so, and the probability of getting such an excitation is can be written as basically proportional e to the minus the energy of this excitation divided by temperature. And so the next question is, the excitations of interest are vortices. So what happens to these vortices? They're excitations. So at low temperatures in a superfluid, of course there will be vortices floating around. But you can imagine these vortices are basically paired up, where one pair I've got a clockwise circulation, the other vortex I've got an anti-clockwise circulation, and I've got two of these animals close together, and if I look at what's happening a long way from these excitations, the answer is nothing's happening. And so of course we can have excitations where we've got, if you like, vortex-anti-vortex pairs floating about, because these configurations have they've got a finite energy, but it's not that high. So there will be statistical mechanics immediately tells us, yes, there will be these pairs of excitations, but they'll be floating around and according to some thermal distribution, but they don't do anything. They're just there. So you can still have a superfluid flow. Then, if you increase the temperature, but remember these vortices are the animals which will eventually dissipate the flow. So then statistical mechanics tells you if you in equilibrium, if you increase the temperature, these vortices will tend to drift further and further apart, and eventually at above some temperature, some of the vortices will actually be, if you like, free. They will, in equilibrium, drift apart so far that they basically don't feed each other anymore, so they're basically free. And if we have a system of this superfluid with a finite concentration of free vortices floating about in it, then as soon as you start the flow going, these things will drift to the sides of the system and will dissipate the flow. Therefore, the difference between a superfluid and a normal fluid is defined by the presence or absence of free vortices. And exactly the same thing can be argued about a crystal can be defined by the absence of free dislocations. Whereas if you have free dislocations present, this system, if you try to shear it, the shear modulus will go to 0 because these dislocations can then drift to the sides of the system, and the system can be sheared with no force applied, and such a system has to be called a fluid. So the melting problem can be argued to be just like the superfluid problem, but somewhat more complicated. Now, of course, all right, I see that I'm running out of time now. So let me summarize by saying that the superfluid system I've talked about, and it's well understood now. And this experiment by Bishop and Reppe can say that, yes, we can say that the theory of vortex theory is well confirmed. The same sort of thing can be said with the melting theory with dislocation. Let me just flick through. I've got some slide here. Oh, there we go. Here is a summary of the experimental measurements, comparing experimental measurements with some detailed theory based on dislocations. And you can see that, okay, the experiment and the theory actually agree surprisingly well. And so we can say that this represents a nice confirmation of two-dimensional melting by the defect, this topological defect melting theory. And so for the two systems which can be parameterized by a set of so-called topological excitations, vortices in the superfluids case and dislocations and so on in the melting two-dimensional crystal melting case, both of these systems are well explained by a theory which is not unreasonable in the case of superfluids and much more complicated in the case of two-dimensional crystals. But experiment and theory agree remarkably well. And so the whole field of the defect-driven phase transitions in 2 dimensions, one can say is rather well confirmed. Now, I think it might be a good idea for me to stop there, and I am happy to try to answer any questions. Thank you for your attention.
Before coming to the question session, I would like to give a little bit of a local flavor on the story which we are seeing here and hearing about. It started with the Merman-Wagner theorem, saying that you will not get a long-range order in a 2D XY system, which which we have been hearing about. Now, then Katie came around, and only later in the 90s, this was really rationalized in things that I understood. The question is, how big is infinity? If you take, for example, 2D XY system, magnetic system, the size of Sweden is still not infinite enough to get m equal to 0. So, yes, when you go to the lab with your 1 square centimeter with a 2-dimensional XY magnet, you can be pretty sure that you're going to see some ordering there. And that is just a local perspective, and we see fantastic progress now going to nanomagnetism, utilizing these ideas, once again illustrating the beauty of the wall of knowledge which is being built. Thank you. Questions?
There must be some, because there are a number of... You'd be surprised how few people really understand the theory. And so there must be some questions. Please, don't be afraid of illustrating that you don't understand much, because it is difficult to understand.
So maybe I can... Is it on? All right, so maybe just to set people off, then I'll ask a question. So first of all, thank you very much for a very, very interesting presentation.
You're welcome.
So most of your experiments and the experimental motivation, that was in superfluids and experiments done in superfluids, but the models that you used were models that are not really naturally connected to superfluidity. Of course, the order parameter then becomes that, but it's really models of magnetism, and you have spins coupling and actually Ising models. So maybe you can say just a few words about that connection.
Okay, I was trying to, I tried to mention that these class of magnetic models, which are useful theoretical models, can be mapped into real non-imitation experimental realization. For example, if you consider a 2-component model, if you like, that corresponds to a complex field, this is exactly the problem of a thin film of helium, thin superfluid film. And of course, we're saying that a thin superfluid film, 2, 3, 4, 5, 6 atomic, 6 atomic length thickness is 2-dimensional, which is not an unreasonable approximation. Then there are another set of systems in the this planar rotor problem, magnetic problem, is known that can be mapped exactly into the superfluid helium problem. I'm not going into this mapping because that would take a long time to explain. It's also not of importance here. But this class of magnetic models is a commonly used theoretical toy playground. of course, more complicated systems like two-dimensional crystals, they can't be obtained from a simple magnetic analog. But the two-dimensional melting problem or crystal problem is better thought of in its own, by itself. And the standard, or at least the best way of looking at that is to write down the linear, say the free energy is given by a linear elastic free energy, quadratic in the displacement. And then you add in the topological excitations, dislocations, and disclinations, and carry out the same sort of manipulations as you do in the simpler superfluid case. It's exactly the same ideas, and the results are basically exactly the same, except, of course, in the melting problem case, it's much, much more complicated. So that's really, I hope, okay.
Any other questions? Please use the microphone.
I've been reading a lot about magnetism in this context, and where does magnetism come in this subject? Because you said something about
it. Sorry. Magnetism is the magnetic models are only used as toy models. The point is that the physical system has to be can be mapped, at least for the superfluid situation, superfluid film situation, can be mapped exactly onto the magnetic problem with a two-component spin. So, I mean, at the time we were looking at studying this problem back in the 70s, a long time ago, we were interested in the phase transitions, and magnetic models were the standard theoretical playground to study phase transitions. So we just waved our hands and said, okay, the superfluid case can be modeled in terms of a two-component classical spin system. So let's look at that one. So, I mean, the connection between, there's no real connection between magnetism and the systems we're looking at, except that the magnetic model can be used because it's an exact mapping from the physical system to the magnetic system.
You have shown and explained how phase transitions in 2D films can occur. What about timescales? I mean, timescales for phase transitions are extremely important in applications like computer memories and so on. Is that something that you can somehow?
No. You see, if we talk about the theory of a phase transition, a theorist doesn't care if things happen in a microsecond, a nanosecond, or the age of the universe. Because the question we were trying to address was whether or not a phase transition occurred. Of course, the timescales, as far as the theorist is concerned, are irrelevant. It may be a bit expensive to keep a graduate student for 100 years in order to make a proper experimental measurement, but that's not our problem, that's the experimentalist problem. So it's really a matter of practicality, what can be done and what can't be done. Okay.
I think we close the session now, so let's thank Michael Kosterlitz again.
Thank you.
But before leaving, we have to do a duty, which is a long tradition, and my colleague is going to explain all about it.
Thank you for so I guess this is on, do you hear me? Thank you again for a very nice presentation, and of course congratulations.
Thank you.
To the Nobel Prize this year. That's a wonderful thing to do, to achieve. I think for most you don't hear me? You want me to have it even closer. I think for most scientists, being awarded the Nobel Prize is a true honor. It's extremely difficult to get there. And I would guess that at the time when you did this work in the 70s, you had no idea that in 40 years I'm going to get the Nobel Prize for this.
Of course not. Because when we started this stuff, at least from my point of view, I could just see it as an entertaining and very difficult theoretical problem. I don't think even David Thales had much idea of where it would eventually, how widely it could be applied to so many different systems. I mean, it's even been applied to cold, experiments in cold atoms. And the theory and experiments, at least if you plot the right quantity, agree to within, at some accuracy, which is not as good as one might like, but the trends look right. So in that sense, we can think that this theory can be applied to a whole slew of different systems. Thin superconducting films, melting of two-dimensional systems. Some aspects of cold atoms, at least when you make two-dimensional systems of cold atoms. And probably a few others as well. I mean, thin film superconductivity. And who knows what the future will bring? I mean, there are so many.
Oh, sorry.
Yeah, go on.
No, I think that's exactly. Who knows what the future will
bring? Right. I mean, there's so many very smart experimentalists around that they will. I'm sure they will come up with yet more applications.
And I think one thing that I'm sure you didn't know this morning, and but that you will know in a few seconds, is if you have become a Nobel laureate and you also come here to Uppsala to present your research, you also become an honorary member of the Uppsala Physical Society.
Wow.
So I'm happy to give you an honorary membership.
Thank you very much.
Which includes a diploma.
Thank you.
And it's also the Ångström Medal in silver.
Okay, thank you so much. Wow.
And we take a little bit of time to say that this is, as far as I know, the only scientific achievement that is slightly more difficult to get than the Nobel Prize itself, because you actually have to come here.
We cut here, and thank you all for coming, and I hope you are inspired to do great things in the lab in the years to come.